Every model in the artificial intelligence landscape serves a specific function based on the data it was built to process. We begin in the classical machine learning sector. Historically, organizations struggled to find patterns within millions of rows of spreadsheet data because human analysis was too slow to process that much structured information. This grid transforms into a flowchart to represent supervised learning, which learns from labeled examples to predict a specific target. To predict a continuous number, like a house price, researchers use linear regression. To categorize tabular data, decision tree ensembles route data down if-then paths, remaining the standard for spreadsheet-based predictions. When the target isn't known, unsupervised learning identifies hidden patterns in raw data. As these data points move into clusters, algorithms like k-means identify similarities across the dataset, providing a mathematical way to segment customers based on their behavior. While classical machine learning organized records and databases efficiently, these tools lacked the architecture required to interpret the messy, unstructured reality of the physical world. Traditional algorithms fail when processing raw data, like photos or audio clips. Deep learning was developed to handle this complexity. As the image shatters into pixels, it flows into a multi-layered neural network mimicking the human brain. Inside a convolutional neural network, a distinct square filter mechanically slides across the image grid, scanning for edges and shapes. This capability is evident in self-driving cars, which use CNNs to track pedestrian signs and navigate the surrounding road environment in real time. Similarly, TSA identity verification systems utilize CNNs to extract biometric features from a camera array, turning unstructured visual data into a verified identity. Other specialized architectures handle non-visual data. On the left, RNNs and LSTMs use repeating memory loops to process sequential data like speech. On the right, graph neural networks, or GNNs, map interconnected nodes to analyze molecular structures for drug discovery. Consider two tasks: analyzing a molecular structure for medicine and detecting a stop sign from a dashboard camera. As the diagram shows, a graph neural network handles the complex molecular map, while a CNN processes the visual data from the road. While deep learning excels at understanding and categorizing data, it is an analytical tool. A convolutional neural network can label a photograph of a dog, but it cannot generate a new image of one. Generative AI moves beyond simple labeling. By learning the underlying mathematical distribution of a dataset, these models populate a blank canvas pixel by pixel to create entirely new content. In large language models, attention mechanisms connect relevant words across a paragraph. This allows the transformer architecture to process entire sequences of data simultaneously to understand deep context. Image generation relies on different architectures. Diffusion models start with pure random noise and gradually subtract it to reveal a clear shape. Meanwhile, generative adversarial networks, or GANs, pit a generator against a discriminator until the model produces results that are indistinguishable from reality. These models provide a mechanism for generating new media, but they are still limited by the specific data used during their training. When there is no static dataset, models must learn within an interactive environment. Reinforcement learning uses trial and error, where the agent receives rewards for successful actions and punishments for failures, such as hitting a wall in a maze. Classic video games served as the testing ground. By combining reward systems with neural networks, deep Q networks mastered complex environments like these Atari titles. Algorithms like proximal policy optimization take this further, providing the stability required for robotics, and for fine-tuning the behavior of language models like ChatGPT through human feedback. This represents the shift toward active environmental mastery, where the AI learns to refine its behavior through direct experience. The complete map covers 4 distinct territories: analyzing spreadsheets, interpreting images, generating content, and navigating environments. These 4 pillars, classical ML, deep learning, generative AI, and reinforcement learning, form the foundation, each solving a specific data challenge. Understanding which specific tool is required for a given problem is the most effective way to navigate the evolving world of artificial intelligence.